Next is going to be a titration curve for a weak acid and strong base. So this titration curve is going to represent 40 mils of a 0.100 molar weak acid with a 0.100 molar strong base of NaOH. Now the weak acid is going to be propanoic acid, and they give us HPR as the formula for it. Now, of course, if it's going to be a weak acid, it has the ability to disassociate slightly. And if it disassociates slightly, that means, yes, we do have a Ka value. You can go ahead and use a Rice table to get the concentration of H3O plus, and then go further to get the initial pH. And that initial pH should be rather low because we're dealing with a weak acid. As we continue to add strong base, guess what? There's going to be a gradual increase in the pH, but we actually create that ratio between weak acid and its conjugate base. And anytime you create that ratio, you can go ahead and focus on the Henderson-Hasselbalch equation, which means the pH is equal to pKa plus the log of our ratio or our buffer components. Why do we have buffer components? Because again, a weak acid has the ability to slightly disassociate, and therefore it has the ability to form its weak acid and conjugate base and that buffer region ratio. Now, guess what's cool about this buffer region? The midpoint of this buffer region is going to be a point where the ratio here is equal to 1. And so the log of 1 is simply going to be 0. And so that midpoint is going to be an area where the pH is actually equal to the pKa for this weak acid. So on the titration curve here, you'll see the buffer region kind of blocked out. And then the midpoint here is going to be where the volume is and that pH, whatever pH we have here at that midpoint. Now, of course, OH is going to continually be added until all the HPR or the weak acid is used up. Once all the HPR or weak acid is used up, that means any added amount of NaOH is also going to equal to whatever amount of HPR you had. So if all my HPR is used up, I'm probably going to be left with this conjugate base. And so you're basically going to take its conjugate base and therefore mix it with water, and you're able to go ahead and go forward to get the concentration of, say, OH minus. Then you can go further to get the POH, and then of course you can go further to get the pH. And at this point, you will see that the pH is way higher because we are basically having a basic solution since we're left only with the conjugate base at that point. Now, if I continually add more and more base, what's going to happen? My pH is going to continually increase slowly but surely, and any excess OH minus I have to now account for in my calculation. Let's focus on calculation. So first things first, we have to get our initial pH. We're dealing with the weak acid, so yes, we will have a Ka value. It's going to be our products divided by our reactant, or you see our conjugate base divided by our weak acid, and of course our conjugate base is multiplied by the H3O plus concentration. You can go ahead and get a Rice table here. Once you have your Rice table, you can get your H3O plus concentration. Once you have your H3O plus concentration, then you can go forward and get your pH. And of course, that's going to represent number 1 here, or our initial pH on this titration curve. To get our pH for the buffer region, what we're going to do is first get our new initial amounts because we're adding OH. And so since you're adding OH, you know you have to get your new initial amounts. You definitely need to do a Rice table here. And of course, OH minus is going to be used up. So if OH minus is used up, it's going to allow you to then go ahead and figure out how much of your acid you have left over and how much of your weak base you also have that was produced. Once you have your new initial amounts from this Rice table, you then can use them in the Henderson-Hasselbalch equation and go ahead and get your pH. Of course, at the equivalence point, you then have to, again, account for the fact that you're adding in that added OH minus, and so now you definitely have to get new initial amounts. If you're getting new initial amounts, you know you're going to be dealing with a Rice table again. This time, you know that your weak acid, which for us is going to be HPR, and the OH minus that's added are going to be used up, and they also should be equal to one another, okay, because we're at the equivalence point. What you're going to be left over with is your conjugate base. Once you have your conjugate base, therefore, you can go forward and create a new Rice table to get rid of the conjugate base and produce OH minus. And of course, since you're dealing with the conjugate base, you have a Kb value here. And of course, if you want to go further and get a Ka value, you could use Kb is equal to Kw divided by Ka. Either way it goes, once you get this new initial amount of your conjugate base, you're going to have a brand new Rice table to solve for the concentration of OH minus. Once you know the concentration of OH minus, you can go ahead and get the POH. Once you know the pH, you can POH, you can go ahead and get the pH by taking 14.00 minus the POH value you got. And of course, after the equivalence point here, if you want to get the pH when you are adding excess base, then since you're adding base, you have to first ask yourself, well, let me go ahead and get my new initial amounts. Once you have your new initial amounts, you know you're going to be in rice table land. Once you're in rice table land, you have to ask yourself, what's going to be used up? Well, we definitely should have no weak acid, so that weak acid should be used up. Okay, you definitely will going to have excess OH minus, and so the excess OH minus we want to account for, and you should have some of the conjugate base produced, but we're not really focused on that, right? We're focused on the excess OH minus because that's what's going to contribute most to any changes in pH. So we're going to do our rice table. We're going to get our OH minus concentration. We're going to take the moles of OH minus in excess and divide it by the total volume. Once you have this concentration, you can get the POH. Once you have the POH, then you can go ahead and get the pH just like we saw before. So for weak acid strong base titrations, because we're dealing with the weak acid, we have to be doing rice tables at every step. Whereas before, when we had a strong acid and strong base, there was not rice tables at every step. And so the work for weak acid strong base is a lot more involved, which is why we're going to get into a calculation of this next. All right, folks, we're back at the Avengers compound. And what does it say here? It says calculate the pH during the titration of 40 mils of a 0.1000 molar propanoic acid. So we're dealing with HPR again, our weak acid, and they give us a Ka value of HPR after adding the following volumes of a 0.100 molar NaOH base. And so the NaOH is going to be our titrant. The HPR is going to be our analyte. And essentially, you're going to be having your NaOH inside of your burette. And then you will have your flask with your HPR. And the goal is to get to that equivalence point and then, of course, do calculation. So they want us to calculate the pH initially at 0.00 milliliters. After 30 mils of NaOH is added, after 40 mils of NaOH is added, which equals the amount of the analyte that we started with, or our weak acid. And then after 50 mils of NaOH is added. So we have letter A, which is going to represent the initial pH for our weak acid strong base titration curve like we saw in the previous portion. And then letter B is going to represent that buffer region. Letter C is going to represent the equivalence point. And letter D is going to represent when we have excess NaOH. So what we need to do is set everything up. So yes, that means for part A, I got to get my Ka value to get my pH. Yes, that means I have to have my rice table and get my pH and use Henderson-Hasselbalch here. Yes, that means I have to get my new initial amount, get a rice table multiple times in order to get the pH. Yes, I have to go ahead and get a new initial amount and again, get a rice table to get my concentration of OH minus. So it is a lot of work for this portion, okay, folks? That's why it's best that we're going through an overall example here. Is it going to be a very long example that you see in your exam? No. Could it be something you see in the homework? Yes. Since we're starting off initially, that means we're going to mainly have a solution that are going to be our weak acid. So I'm going to take my weak acid, which is propanoic acid, HPR, mix it with water for my reaction for my rice table to produce H3O plus and its conjugate base. I'm going to fill in my rice table. I know the initial amount is 0.1000. That's given here. I know that I don't know my product amounts and water does not matter for our rice table. So then I get 0.1000 minus X as my equilibrium amount. I therefore make an assumption for X because when I look at my Ka value, I see that it's times 10 to the negative 5. And so I can make an assumption there. All right, folks? So I make my assumption, then I set up my Ka expression. It equals my products divided by my reactants. I know this is equal to 1.3 times 10 to the negative 5. That's going to equal to X squared based on my products divided by 0.1000. I want to then solve for X, so I take the square root of my Ka value multiplied by my HPR value, and I get my H3O plus concentration. It's 1.1 times 10 to the negative 3 molar. If I want to get pH, all I have to do is take the negative log of that, and my pH is therefore going to equal 2.96. For part B, we're adding 30 mils of a 0.100 molar NaOH solution. So effectively, we're adding OH minus to our acid-base titration. So what we need to do is get the moles or initial moles of NaOH and initial moles of our weak acid HPR. And since we are dealing with our buffer component ratio, then the volume is going to cancel, so there's no need to have molarity here. You can have moles. So therefore, in order to get my moles of NaOH, I'm going to take my volume of NaOH that is going to be added in liters, which is 0.03000 liters, multiplied by the concentration of NaOH. When I multiply these numbers, I get my moles of NaOH, which is 3.00 times 10 to the negative 3. I will do the same thing for moles of HPR. I'm going to take my 40 mils put it into liters, multiply it by the molarity given, and I get 4.000 times 10 to the negative 3 mole. I then set up my rice table. I have my weak acid, but this time it's not the initial pH. It's going to be mixed with OH minus. So I have HBr mixed with OH minus. HBr is going to donate a proton to OH minus to form water. What's left over is its conjugate base, PR minus. So I therefore set up my rice table. I have my initial moles, which I just calculated up here, 0.00400. Of course, this is just what it looks like in non-scientific notation form. I did the same thing for my OH minus, and for my conjugate base, it's going to start at the product of 0, right? I have minus X and minus X. Now remember, I'm adding OH minus, so it's going to be used up completely. Therefore, the concentration of OH minus at equilibrium is going to be 0. If I then solve for X, my X is going to equal exactly whatever the initial amount of OH minus is. So instead of putting minus X here, I'm going to put minus 0.003000 so that I can get 0 for my overall equilibrium amount. Now again, if my X is equal to 0.00300, therefore my conjugate base is equal to plus 0.00300. And of course, my HPR, or my weak acid at equilibrium, is going to be 0.00400 minus X, which we know is 0.003000. And again, what I get as the final answer for my HPR at equilibrium is going to be 0.001000. Now, I have brand new initial amounts for HPR and a brand new initial amount for my conjugate base. And so because I have my initial amounts and they just simply want to know pH, I can use the Henderson-Hasselbalch equation here because I know I'm in a buffer region, right? So pH is equal to pKa plus the log of the base divided by the acid. My base is 0.003. My acid is 0.001. Those are my new initial amount. My pKa is going to be the negative log of whatever my Ka value is. My Ka value is 1.3 times 10 to the negative 5. And so when I take the negative log of that, I get 4.89. When I take the log of 0.003 divided by 0.001, I get 0.477. And so to get a pH for letter B, I get 5.36. Again, we have to start with initial amount, got a rice table, got new initial amounts, and then use the Henderson-Hasselbalch equation to get pH. Let's go on to letter C. For letter C, we're adding an equal amount of NaOH base, of course, at the same concentration, to 40 mils of our HPR weak acid analyte solution. Okay, folks? And so therefore, we are at the equivalence point. All we need now is to do calculations at the equivalence point. So first, because we added NaOH, let's go ahead and get our moles. So the moles of NaOH and the moles of HPR are going to be equal to one another. So I got to take my 40 mils, put it into liters, and multiply it by the molarity. I get 0.004000 moles, okay? I'm going to put that in a rice table. Remember, we have our weak acid mixed with OH minus to produce water and its conjugate base. Now, because we're at the equivalence point, if I'm adding OH minus, we know that's going to get used up and become 0. But also HPR should be 0 as well because there should not be any more of it left over. So at equilibrium, HPR and OH minus are both going to be 0, and so therefore our X value is also 0.00400. And that means the PR minus, or the amount of moles of PR minus, or the conjugate base left over, is 0.00400, okay? So if we want to go further and get the concentration of our conjugate base, so that means we take our moles of conjugate base and divide it by the total volume. The total volume is 40 mils of the acid plus 40 mils of the base, which equals 80 mils. So we take 0.00400 and divide it by 0.08. That means the concentration of PR minus at equilibrium is going to equal 0.05000 molar. We then take our conjugate base, which we know has the ability to react with water, and we set up another rice table to solve for the OH minus concentration. So we take our conjugate base here, mix it with water. It's going to be at equilibrium to form HPR, which is the weak acid again, and of course OH minus. We're going to solve for OH minus to get the POH value. And of course, once we get our POH value, we can get the pH value. So we plug in our new initial amount that we got from our initial rice table. We have our minus X value, and then we have our 0.05 minus X. Now our minus X here, we can make an assumption because our KB value is really small. But you have to ask yourself, where'd you get the KB value? We're only given Ka. Well, in order to get KB, you're going to take Kw, which is 1.0 times 10 to the negative 14, and divide it by your Ka value, which is 1.3 times 10 to the negative 5. That's going to equal 7.7 times 10 to the negative 10, which again is a small enough number that we can make an assumption. So all we do now is use this rice table to solve for x. Okay, so we have our KB is equal to x squared divided by 0.05 from our rice table. To solve for x, we take the square root of both sides, and we're going to take our KB value and multiply by 0.05, right? So in order to solve for x, I'm going to take the square root of 7.7 times 10 to the negative 10, which is my KB value, multiplied by 0.05. I get 3.85 times 10 to the negative 11. I take the square root of this number, and I get 6.2 times 10 to the negative 6. I've effectively solved for x. If I solve for x, then I automatically have solved for my OH minus concentration. To get the POH, I'm going to take the negative log of that concentration, which is the negative log of 6.2 times 10 to the negative 6. And what do I get? 5.21. Now that I know my POH, I can solve for pH, which is going to equal 14.00 minus 5.21. Therefore, my pH is equal to 8.79. Let's go ahead and go to part D. For our final letter, we're going to be adding 50 mils of the 0.1000 molar NaOH. So we're adding excess base. So that means we have to get our moles because we have a different volume. So the moles of NaOH is going to be 0.05 times 0.1, which is going to be 0.005 moles. Moles of HPR is still going to be 0.004000 moles, okay? We're going to set up a rice table. We have our weak acid plus OH minus is going to produce water and its conjugate base. We add in our initial amounts, but this time, since we already passed the equivalence point, we do not have any weak acid. So the weak acid is going to completely be used up here. And so the equilibrium of HPR is going to be 0. Therefore, our X value is also equal to 0.00400. And so I'm going to plug in the X value for all of the other portions of the rice table. That means the OH minus, we started out with 0.005, 0.004 is going to be used up. Therefore, at equilibrium, you're going to have 0.00100 moles of OH minus left over. And then for the conjugate base, you're going to have 0.00400 moles left over as well. To get the amount of OH minus that's going to be in excess, we take the mole that we got from our rice table at equilibrium and divide it by the total volume. The total volume is 40 mils plus 50 mils, which is equal to 90 mils. Convert that to liters, and I get 1.1 times 10 to the negative 2 molarity. Now, once I have the concentration of OH minus, I go ahead and get the POH, which is the negative log of 1.1 times 10 to the negative 2, and I get 1.95. To get the pH, I'm going to take 14.00 minus 1.95. And what do I get? 12.05. And so that is the pH for letters A through D. Again, very involved, so you have to make sure that you're going step by step with this information, asking as much questions as you can, and of course, gaining information from the titration curve itself. Let's move on to the next, folks.